Hi, this is Rob Bolaños. Welcome to the analysis and design of a flyback converter. This is part 22. I'm going to start getting into designing with the TL431 and a optocoupler. Many of you have been asking for a video or information on this, and I've been researching it, and it looked like it was a little bit complicated, but after seeing it, there are a lot of similarities to what I've already taught. So I'm going to go ahead and try and make this a short video. It's going to be just on the TL431, how it's used as a shunt regulator, and then hopefully how the shunt regulator is used with the opto, and then how to use both the TL431 and the opto with the flyback. Okay, so you can have isolation. Okay, so we're going to try and see if we can do some simulation, see how the TL431 works, how you can program it. Maybe not in this video, but certainly on the next one. I'm going to use it in the opto feedback, and then we're going to compensate it as well. Okay, Googling and researching a little bit on the TL431, I managed to find a picture of the T431. Here's a die. Someone actually took one apart and debonded it and took a picture of it, and they have some of the components there. You can see capacitors, you can see some it looks like a BJT and so forth. Anyway, this is the picture, and like I said, it's a shunt regulator, or can be used as a shunt regulator, but it's really a programmable zener. Okay, so this is the equivalent. Okay, if I draw the symbol, looks something like this. So this would be the ref, this would be the cathode, either C for cathode or a K, and then this is your anode. So this is a representation, and what this is telling you that the TL431 with the 3 terminals is internally has a opamp. It's got a reference. This reference is typically 2.5 volts. Okay, and it has a shunt transistor. Okay, in this case it's NPN, and has a diode across the cathode and the anode. Okay, so we got that. Okay, so what I try to do is I want to show the equivalent, that these are in fact equivalent. Okay, and one of the simplest way of using this is if you connect the reference and connect it to its cathode. Basically, you connect it in this configuration. Now mind you, if you look at the specification, let me look at this here. This is the specification, and let me see if I can make this a little bit bigger so we can see this. Okay. The most important specification that you want to look up is this one, VREF, and VREF is 2.5 volts. Okay, so what does that mean? It means that the voltage Vref in reference to ground, in this case the anode being connected to ground, is going to be equal to 2.5 volts. Okay, so I'm not sure if this is obvious or not, but if this is 2.5 volts and you connect this to the cathode, and then if you put a resistor up here, then the cathode will also be 2.5 volts. Okay, so I'm going to do a simulation to show that as well. Okay, so then what I did is I did a representation of this TL431 using a reference, an opamp, and a bipolar transistors. I left the diode out, and then these disregard. These are to measure current, so just think of them as short circuit. Okay, and if I run the simulation, or I should already have it, if I run the simulation right here, notice it's connected to the cathode, and when I do a DC operating point, it says that it's 2.449 volts. Okay, so basically I do the same thing here. Here I have this resistor as 1T. 1T is basically open. This resistor I made it a 1 ohm resistor. It could be 1 milliohm, but the point is it's a very low resistance. And if you look up here, it's also 2.5 volts. Okay, so basically this you can think of is really a zener. You can also think of it as that, a programmable zener. Okay, that's another way. And then I'm going to use that, like if it's a potentiometer, meaning that you can adjust the voltage on that. Okay, now saying that it's programmable, how do you make it programmable? That's a good question. Okay, so we're going to try and do that. And before I do that, let me say, I've already covered this, that when the reference pin is connected to the cathode, that you're going to have to, that you have a 2.5 shunt regulator. I saw that. One of the disadvantages, it cannot drive a large current or low resistance, so that's a disadvantage of that. But an advantage is, as far as power supply is concerned, it is used with an opto to control switching power supplies. Okay, so we're talking about programming it, and to make it programmable, then what you do is you insert two resistors. Basically you do a divider network. Okay, now this is the transfer function. Okay, but I wanted to see if we could derive it. Derive the transfer function, TF. Okay, so we're going to do this. It's labeled. Okay, so the first equation that I need is this one. Okay, meaning that the voltage at this point is going to be 2.5 volts. Right there. Okay. Okay, so let me go ahead and write this one. I'll write it again. Okay, and then IREF is the current that is going into the op-amp, the internal op-amp that's in there. Okay, now we can also express VREF in terms of R2. So we can say that Vref, or actually the current, this current, let me change colors, turn green. We're going to label this as IR2. We can say that Vref is actually, let me do it correctly. We're going to say that the current through R2 is actually Vref divided by R2. Okay, so that's one current, this current. Okay, and we know we have this current here going or coming out of this node. So then we have this current, and this we can say that it's IR1. Okay, so just by looking in here, we can say that IR1 is equal to the product of these two, or the summation of these two, which is IREF plus IR2. Okay, so now we have one equation, two equations, three equations. Okay, so what I'm interested is, I want a V out here, and we can say that this is going to be V out. Okay, so now I think we may be able to write an equation. Okay, so if we take this loop, okay, we can say that it's, and let's label the voltage drops. Okay, I'm going to use conventional current flow theory. It's going to go in this direction. So then I can say that V out is equal to IR1 times R1 plus IR2 times R2. Okay, so now we can express this, put that there, and then put this in here. Okay. Okay, so I'll bring the R1 first. IREF IR2, and then I'll say R2 is equal to Vref R2. Okay, now there's another substitution that we can do. If you notice, we can also plug this in there. So let me go ahead and do that. Vref R2. Then we have Vref. Okay. Okay, so let's go ahead and distribute the R1, R2, and then this is going to be R1, R2, Vref plus Vref. Okay, does that look right? Okay. Actually, there's an error here. Is that right? Yes, this looks right. Okay, so now I can factor this out. The VREF, I'll bring it over to this side, to the left side. We'll say that VREF 1 plus R1 R2 plus R1 RF. Okay, so is that the same equation? It should be. Yes, that's the same equation, IRF. Yeah. Okay, so I got it right. Okay, so that makes sense. Okay. So that's the transfer function, and I just showed how it is derived. Okay. Now, hopefully, I'm not sure if you are familiar, but that equation is very similar to when you use Okay, so this is a inverting opamp. Okay, and if not sure if you remember, the equation for this is so basically it's kind of like an opamp. So that's another way of thinking about it. Okay. The only difference is that this has a term, and typically this is small. It's usually 2 microamps. So this is typically small. So the dominant is going to be that. Okay. So let's see if it works. Okay. So let's go to the simulation and let's make it programmable. Okay. So if we want, we know that this node is VREF. So let's go ahead and put a resistor. Let's just make it 1K just for the heck of it. Let's put another resistor here. So it is a voltage divider. Okay. And basically it's the ratio of this divided by that, which is 1, plus 1 is 2. Okay. Let me go back. Right. Okay. So if we make this 1 plus 1, and it's 2.5, so this is 2 times 2.5, and we're going to have 5 volts. Okay, so let's take a look, see if it does work. So I should have 2 volts here. Okay, so let's do the same thing here. Let's put 1K, 1K. Okay, so now we run it. Okay, so hopefully you should have 5 volts. So why am I not getting 5 volts? I'm getting 4 volts here. What is happening? Y'all have any guess? Okay. Well, let's take a look at this. Okay, if you notice, you have this loop, this resistor. This resistor is supposed to be the shunt regulator, or the series. This is your shunt. Okay, so this will only regulate it. So what about if we make this 5 in order to pass more current? Okay. Oh, I made it bigger. Okay, let's make it 1,000. Yep. There we go. Let's see what we get. Voila. Okay. So you have to have enough current supplied by your series resistor. So let's go ahead and change this. Okay. Let's go ahead and make both of them the same. 1K. That way there's enough current capability. Okay. 4.992, 5 volts. Okay. So this here is actually, this opamp works a little bit better because the opamp that's inside has a lot more gain than this here. Okay, so that's very important. Okay, so what I want to do, just wondering out loud, if we can measure the loop response of this. Okay, so now if you notice, this voltage here is 4.992. It's about 8 millivolts lower than this. So this means that this has an error, 8 millivolts error, and that error is due because the gain of the TL431 is not as high as the gain of this op-amp. Okay, so one way to measure is to break the loop, and the loop is right here. This is the feedback loop. In this case, here's the feedback loop, and what you do is you insert a voltage source, and I've inserted another voltage source here as well. Okay, so now we can go ahead and type the SPICE directive. We can say calc, which means that it calculates, and I'm going to label it as loop is equal to V out divided by V in. Okay, and then I wanted to plot and we'll put a auto plot. Okay, and we'll say dB, this bracket, close the bracket. Okay, so let me turn this off. Okay, because I want to display the loop of this first one, and we have to do an AC analysis, so we'll put that as 1, and then we have to label. That's out, in. Okay, so what I'm doing is, this is the loop, and this generates a little small signal. That signal comes in, and then it comes out, and it re-enters, and I'm comparing the amplitude of this divided by that. That would be the gain. Okay. You can also do the phase. Let me type this. Let's plot the phase as well. And we'll say P for phase. Okay. And we'll do a simulation AC from 1 to 100 megahertz and 10 points per decade. It didn't like that. Let's see, why not? dB, does it have to be capital? Auto clock. Oh, okay. It's auto plot. Plot. Okay. Does it work? And it does. Okay. So here, let me go ahead and take the phase off. Okay, so this is the gain. So this is in dB. Okay, so this is a gain of 50. So 40 is 100, and a 60 dB gain is 1,000. So it's in between. Okay. So now let's compare the gain over here. All we have to do is bring this label there, that label there. Okay, I disable, I enable. Okay, and let me go ahead and save this. I'll save it. Okay, so then let me delete this. Okay, so now we're going to go ahead and run. And there you have it. Notice that this has a much higher gain. So your errors are nulled out with much higher gain. Okay, so we're going to go ahead and add. And here's a comparison. Okay, so that's one of the disadvantage of using the TL431. It does have a internal opamp and an internal reference, and it's good to use as a shunt regulator, but just keep in mind that because of the gain, it has a little bit of limitations. Okay, so in the next video I'll show how to hook it up to an opto and do a little bit of a small signals analysis, and then hopefully hook it up to a switching model, and then I'm gonna do a simulation using a average model. Okay,